Yes. These first lessons of the term, they're always a bit funny. I don't know what I'm doing. You don't know what you're doing. No, I do know what I'm doing. Okay, so. Okay, I was told that we need to do the register even though you're deep in with the card, so we still need to sign in. If you want to complain about that, you can do. I won't help you. Norman has made up his mind. Right, and so booklets. I have a book on linear programming, but it's not been printed yet. I mean, you can see the PDF on Moodle, I hope, now. And probably next week I'll have a printed copy for everyone. But yeah, it's in the printing services, and it will be available at some point, but not today. So for today, I only have these, and I like handouts. Who hates handouts? Okay, if you, well, tough luck. And I like them. So please take one and pass the rest on. And we'll have homework problems again, as last year. So yeah, you're expected to solve them between the lectures from one week to another. And if you don't, then at least make sure you know the solution for the exams, because these questions that I put into the homework problems, as you might have realized, sometimes they turn up on the exam again. Okay. But also, I mean, they're good to do every week because that keeps you up to date with what's going on. But if you don't, at least look at the solutions afterwards. These are my office hours for this year. What do we do for assessment is listed there. So homework exercises don't count, but they're good. There are assignments which form 20% of the homework in the end. There's an exam which forms 70%. There's a bit of a complicated rubric on this one, but don't worry about it now. I'll explain later as we come to the exams. And then in the second term, you will have financial accounting lectures. Do you know about that? Nobody told you? The reason this is compulsory for financial math students is because there is this bit taught by John Fry on there is this big part on some accounting methods and stuff like that. But, and that's 10. So there is a test on all this accounting, which is 10% of the final mark. Okay. Any questions about this? That's what I do. What Philip does, I don't know. A lot of simulation, but he will have told you by now, I'm sure. What we do is more linear programming in the first term and integer programming in the second term. Yeah, basically. We saw last year that many problems can be solved by linear programming. And linear programming really is quite useful if you want to do operational research and that kind of optimization stuff. So we'll spend more time on a bit more analysis of what goes on in the Simplex method in the first term. And then in the second term, some of the harder problems that you can't really solve with linear programming, you can solve with integer linear programming, which, other than the restrictions that you have for linear objective and linear constraints and so on, you also want all your decision variables to only take on integer values, and it makes it a hard problem. Okay, but we'll see that in term 2. So that's just the plan. Any questions? But the plan for today is just to start looking at what the simplex method, well, reminding ourselves what the simplex method for linear programming actually did. And that is going to be important because, as I said, we want to do a bit more analysis of the simplex method in the rest of this term. And what kind of analysis we'll see. But first, let's just see if we can still remember how we solve problems like this. Does this problem look familiar? Yeah? It is the chess set problem, where we had small and large chess sets. However, for now, mostly we will just ignore what it was in the legend, as it were. So we'll just concentrate on the actual mathematical bits here. And so for us, it's just a linear programming problem. There's 2 decision variables in this case, 3 functional constraints, non-negativity constraints, and an objective. Do you all remember this? Yeah? Who doesn't know what a decision variable is? I don't. So how did we solve a problem like that? Simplex. Yes, that's already here. That wasn't very hard. How does it go? So what we said was, usually, we needed to transform these inequalities into equations, didn't we? By adding slack variables. Is that right? So this inequality, we added a slack variable and it became 3x1 plus 2x2 plus slack 1 equals 160. Is that large enough for everyone to read? If it's not, just let me know, I can make it larger. And we also had a slack variable in the second constraint, and we also had another slack variable in the third constraint, and we also wanted all these slack variables to be non-negative. And there was quite a hard question in the exam, on the exam last year, which asked you to say what the relationship was between x1s and x2s that satisfy this, and x1s and x2s and s1s and s2s and s3s that satisfy this. You remember that? About 5 people got it absolutely correct. Some others attempted something. Yeah, so it is actually written in the book that you got last year. But to remind you is that whenever you have x1 and x2 that satisfy all these inequalities, then you can find s1, s2, and s3 so that you satisfy all these equations. That's one way. And the other way is whenever you have x1, x2, s1, s2, and s3 numbers that satisfy all these equations and these inequalities, of course, then when you go back and you just plug in x1 and x2 into this system, they will satisfy all these inequalities. So it goes both ways. Okay? And that's why we can do it, because originally we were not really interested in solutions to this problem, but we can see that any solution to this problem also solves that problem, and that's good, and vice versa. Any solution of this problem, we can add some S's so that it would solve that problem. So we're not losing anything, and we're not getting anything extra, and that's exactly what we want. All right? Well, so now the last thing we did was we said that this was equal to Z. Z is the objective, usually we call it Z. And then we added an equation which said that Z minus 15x1 minus 20x2 equals 0. Okay. So now what we want to do for this year, we want to rewrite it slightly differently. Because what we want to do is be a bit more generic about what we write. So we don't really want to analyze the simplex method on particular numbers, but we want to have some theorems that work, some observations that work for any problem like this, not just for a particular one with concrete numbers. So, and for this, we'll use a different notation often, which goes like this. So these inequalities that we have here, we can rewrite in the following way. We can write 3, 2, 1, 4, 1/2, and 1/2 in the matrix. And we can put x1 and x2 as a matrix. So what do you get when you do a matrix multiplication like this? Or matrix times vector. Can you work it out? Yes?
Will it just be the 160 to 181?
Minus S1 minus S2.
Ah. You're answering the correct answer to a different question, both of you. Okay, so what I meant was, if you just forget this, okay, just this problem. How would you multiply a matrix times a vector? Row times column, exactly, and then you add them together, don't you? So what you would get here is the first row times the first column gives you 3x1 plus 2x2, and this gives you x1 plus 4x2, and third row times the column gives you half x1 plus half x2. Is that right? So this we can write as 3, 2, 1, 4, 1/2, 1/2 times x1, x2 is less than or equal to 160 to 131. Well, we have to know that less than or equal to between matrices or vectors means that you look at each entry. Okay? So this is that. So what I'm doing is I'm comparing the first entry with the first entry. I'm comparing the second entry here, second entry, and the third with the third. And if they're all less than or equal to, then I can write less than or equal to between the matrices or the vectors. Okay, that's the meaning of this sign in that situation. Now, what would be right with the slack variables? We could also add the slack variables and now it's equal because we changed all the inequalities here to equalities there. Yeah. So now you can see if I do this row times this column, what I'm going to get is exactly this expression. 3 times x1, 2 times x2, 1 times s1, and 0 times s2, and 0 times s3. So I'm getting this. So the first row has to be 160, and then what? And then I have 200 here. And 31 there. So what I'm going to do is call this matrix big A. I'm going to do is call this vector little b. And what I'm going to do is this vector of decision variables, I'm going to call it x. And then what I'm getting was, so the constraints are ax is less than or equal to b, and I also want these to be greater than or equal to 0. So now we have the constraints, we still haven't set what we want to maximize. We want to maximize z. I also want to write the objective, which has disappeared, but it's in your handout, which is 15x1 plus 20x2. If I wanted to write it as a row times a column, what would I do? Yeah. Yes.
Matrix of 1 minus 15 minus 20 times by another matrix of z, x1, x2.
1 minus 15 minus 20 times a column of z, x1, x2. That again is, I'm probably not very good at asking questions because that again is the correct answer to a different question. If I just want z as a row times a column, then I can do it like this. Okay? Because I multiply row by column, I get 15x1 plus 20x2. So I'll call this vector, row vector little c. Okay? Now I've got the whole this wordy thing been transformed into one line. And I'll move it up a little bit because you probably can't see at the bottom. All right. Okay, now I've got this bit here. I don't know what to do with it. No, I'm lying. I know what to do with it. You don't know what to do with it. Yeah? It should be equal to 0, indeed. Yes. So, for the simplex method, we need to add slack variables. So I'll put them into a vector. So I'll take S as the vector of the 3 slack variables. Of course, you won't always have 3 slack variables. You will have as many slack variables as you had constraints in the beginning. But let's stick to this. And now the red box on the left is something. The red box on the right is another one, which we want to have a look at. So the red box on the right, I'll call it star. So the star becomes do you know block matrices from linear algebra? Stephen Lynch. Anybody ever heard the expression block matrix? No? Oh, falling behind in your linear algebra, and it's Steve's fault. Should be telling you. Okay, so the block matrix is just like a matrix, but you put matrices inside rather than numbers. Well, then what you think of is it's just a way of writing things. Okay? Because we know this is A. Okay? You know this is the identity matrix. You know that. So we can write this matrix on the left in this kind of block matrix notation. And you just write A and I. And because you know that A is this bit and I is this bit, AI is this whole matrix. Okay? Is that clear? Times by what? What's this? How do I write it as a block vector?
X and S.
X and S, exactly. And now. B. Yes. Okay, so that's the star. What am I going to call this? Double star. What's the 2 star? The 2 star is one C Z X equals 0. Okay. Ah, but that's not what I want. Okay. Well, this is maybe what I want. I don't know what I want. Do you know what I want? What I want is the answer to the following question. Is it possible to write these 2 matrix equations into one? Not straightforward. Not very hard, right? Yes.
Would you just minus b off the first one so they both equal 0? Each other? Or is that one sort of direction?
Would you just do minus b equals 0 here, and then they would both be equal to each other? No, you couldn't do that.
The first block matrix, like the first equation on the left, if you minus b from both sides, so it's ai bracket xs minus b equals 0, then they're both equal 0.
Now I've lost you. But for 2 reasons you got it wrong.
Okay.
And the first reason is that this b is a vector of well, in our case, 3 times 3. What's it called? 5, 3. Well, 3 and 3. Okay. Whereas the 0 is just a 0. It's not a vector in this case. Well, it's a vector, but it's just one. It's just a number. So they can never be equal. Number 0 does not equal a vector with 3 zeros in it. So there's no way you can make this equal or anything like that equal to anything like that, because they're just different dimensions. That's one thing. And second thing is, if you only did that, you would lose some information. You would get some solution to that new equation that you don't get here. Just requiring that this be equal to that is weaker than requiring that this be equal to 0 and that to be. But what you can do, okay, I'll tell you that. You put your z and your x and your s into one vector. The right-hand side is going to be, I don't know what it's going to be. It depends. What do you want the right-hand side to be? I'll give you 2 options. Number 1 could be b and 0, and number 2 could be 0 and b. Who's for option 1? B and 0? Who wants B and 0? No one. Who's for option 2, 0 and B? No, majority. Which one is correct? You can get both. Well, you voted for 0 and B, so we'll get 0 and B. And now I need a matrix here. So what kind of matrix do I want here? So the first row is something that should give me a 0 when I multiply it with this. So if I want to get a 0, I'm using that. So I want 1 times z c times x and naught times s, right? And then I get naught because of the double star equation. That's the first row. First row times the column gives me the first row here. And then the second row, which actually is many rows, is what do I want z multiplied with? Well, zeros. What do I want x multiplied with? Well, a. And what do I want the s's multiplied with? The identity matrix. And that gives me b. So now this line is what we've got. And what do we call this equation? Yes, this is called indeed a simplex tableau. How do you spell tableau again? E-A-U, because it's a French word. Okay, is this what we call a simplex tableau last year? No. What did we call a simplex tableau last year? This. Is this the same thing? Yes. You've opted for that rather than that, whereas here we had that option first. Okay, because so this is now called B. That's the 0. So we would have actually got that one, but it doesn't matter. You just chuck this row first, or last. It doesn't matter so much. So that is this right hand side. Can you see it there? Yeah. This is A. This is the identity matrix. This 1 and 0s we didn't write, but it belongs there as well. We didn't write it because it never changes. It always stays like that. So we don't have to. And what happened? Okay, and now this shows that I got it wrong there. Where's the mistake? Okay. It should be a minus C. Should be a minus C. So why is there no minus C? Because there's an error somewhere. And I can see it now. Because the 2 star, oh yeah, well, that's the thing. I asked you how to write a star, but the 2 star I wrote myself, so of course it's wrong. Because the 2 star, here we actually had minus C, not C. So apologies, get it wrong right now. So this must be minus C here. And consequently also this must be minus C. Just be careful, this is not like 1 minus C plus 0. These are 3 different entries in our matrix like array. Okay? And this matrix equation. It's actually a block matrix. So, do you believe me now that this is like a simplex tableau? Yeah. Any questions at this point? the right question to ask perhaps at this point is, what is it all good for? Why are we looking at it in this way? And what it's all good for, this is just the first step, because you remember now in this tableau we have to do some pivoting. So what we want to understand next is what is going to be in the Simplex tableau written like that after we do some pivot steps. And after we've done a couple of pivot steps, well, that's the next thing we want to understand. And then based on, once we know exactly what goes on in the Simplex tableau after pivoting, we can do some things with it. And the things we'll be doing with it are of the following form. For example, you want to add a new constraint. So imagine you have a linear programming problem. This is a simple example with 3 constraints, and very quickly you get the solution. But imagine one where you have 1,000 constraints or something like that. So you've already done 3,000 pivot steps maybe, and you got your optimal solution. And then, for some reason, you want to add a new constraint to it. What you don't want to do is just add it and start in the beginning again and do all your 3,000 pivot steps again and get the new solution. What you would ideally want to do is look at the solution that you got in the end and somehow add the new constraint on top of that, in the hope that the new constraint won't change the optimal solution too much. Okay? And in order to be able to do things like this, we want to understand what is where in the Simplex tableau. Okay? That's the goal. So, looking at the clock, I don't know how much more of that we can do. Let's just have a look. So what I'm going to do in the remaining 5 minutes or so is just have a look at what the pivot step would do to remind you. And then next week, what we're going to do is try and express the pivot step in this kind of table form, what it would do to a tableau that looks like that. Okay? That's the plan for next week. And then after next week, we can start doing more fancy stuff. Okay? So what would you do pivoting the old-fashioned way in this table? So you can already see the arrow here. Yes?
So, find the lowest value in the objective equation, then that will show the variable that you're using as the column to form ratio tests for values.
Yes. Okay, so I'll sum up. So the first thing you actually want to do is have a look at whether there are any negative numbers in this row. Okay, so whether there are any negative numbers in what we wrote as the first row of this number. And that there are some negative numbers. Now you pick one of the negative numbers. Well, say you pick the least value in there, which is one way of doing it, but it's not the only way of doing it. But that's the one we usually did last year. So this will be your pivot column. And now you mentioned the ratio test. So what is the ratio test? Look at the entries here divided by the entries in the pivot column. And the ratios are 160 divided by 2, 200 divided by 4, and 31 divided by 1/2. And then you go for the least one. What if there are several least ones? Pardon? Pick any one of them, no matter which one. So in this case, the 50 is the least one, and that indicates that you should do a pivot step on 4. And how does the pivot step go? Well, it divides this row by this element, so you get a 1 there. And then there's row reductions to in a certain way, so that this would be a 1 and all zeros column. So what you want is, we always wanted to protect this kind of property that when you select the objective column and the what we call the basic variable columns, it should, in the right order, it should give you the identity matrix. Okay, so that's what we used to do. Does that sound familiar? Okay, so the pivot step, what it did was divide this row by 4. Okay, I'll add this. Because we want this not to change. This row is just that row divided by 4. And yeah. Now the row reductions have to be done in such a way that you don't disturb these columns. And then you want to keep. So the only way to do that is you take multiples of this row and add them to the remaining rows. Otherwise you would destroy it. Remember this? No, it's not. Not minus. So as I said, the plan for next week to start with is how do we express this kind of pivot step using matrix notation without just and what does it all mean? Got some homework problems? Any questions about anything? Yes?
I'm just looking at the same example, but you did it last year. But you chose -15 for your
Did I?
no, so
Yes, that's what I said. You can choose any of the negative numbers. There's quite a lot of research done on which one you should choose, but it's inconclusive. Nobody knows the best way to do it yet. Yes?
I didn't study RMU last year, so I know nothing about pivoting. Where can I read about it?
Well, you can read about it in the book we had last year.
That's what you were speaking.
So you go and, well, why not? Talk to me after everybody. Talk to me now. All right, okay? Well, then see you either on Friday or next week.